Welcome back to ECE 320A. This is a review session for exam number 1, and the exam is Thursday, the 14th of February. Review material is on D2L in that module for exam 1, and if you're looking for solutions or wondering, did I work these right? I obviously maybe entered the correct answer in mastering, but I would maybe like to see how somebody else might have worked the problem. There are solutions to the homework on those modules or within those modules in D2L for Unit 1 and Unit 2. And those units are the units that will be covered on exam number 1. What I want to do now is simply state what the process of the exam will be, identify some key terms or phrases. What do you really need to pay attention to when you read these word problems on the exam, and then work some example problems. That's the goal for this session. And if you have questions during that time, raise your hand and I'll try to see if I can address your questions. We've talked about the process before. It shouldn't be a surprise. But what I have had students ask is, will this note sheet be provided? No, I am not providing you with a note sheet. You need to come in with your own note sheet, 8.5 inches by 11. It can be front and back, but now it's up to you to decide what you put on that note sheet. It's your note sheet, and you'll be able to keep that, and we may accrue these over the course of the semester. You may get another one for exam 2, and you can reuse or use exam 1's note sheet. But you're only getting one for exam 1. 1 page of notes, 8.5 by 11 front and back. You can bring a graphing calculator, a TI Inspire, a TI 89, an HP 51, but not a computer, even though those are computers essentially. Something to write with. And if you're sketching, which I encourage, you can bring a ruler or a protractor if you want to now start measuring angles or drawing things a little bit more to your liking. You can bring those. What's not allowed, you can't have a computer, you can't use your cell phone, no textbook, and no class notes, and no neighbor. So we'll try to spread out and have you take the exam in this room, obviously, but that's where we're headed. Questions on the process? The structure, I would strongly suggest you look at the practice exam from fall 15. This exam will probably be formatted or laid out similarly. In terms, I think there were 10 problems, and they were each worth 10 points. I'm expecting you to not just write down A or B. This is not multiple choice. It's long answer, and I need you to show your work and to indicate your answer. Box your answer so that I know what you're expecting. And I would encourage, if you start working something and you say, oh, just draw a line through it. Don't spend time erasing. You might find, oh, why did I erase? That's actually mostly right or correct. I want to keep that. So you could just indicate that in your comments. And if you've already erased it, then you've wasted a lot of time. Just draw a line through it if you think it's not important to my grading of that problem. And the problems themselves, you may find several of them very easy, very straightforward. Some you may find a little bit more challenging. They're not all equally difficult, the problems that you'll see. And I would encourage you to draw pictures. Draw pictures of the phase sequence. Draw pictures of, oh, here's a Y-connected load, or here's what I have. Here's a piece of what this problem is stating. And now I need to extract from that useful information or something to get me to the answer. That's the structure. Here are some key terms or phrases that you need to sit up and pay attention to, be alert to when you're reading these problems. A lot of these problems will be descriptions or descriptive, wordy. In a three-phase problem, be aware of total and per phase or each. They're different. If I say the total power, the total complex power, that means for all three phases. If I say the power in a transmission line or in each transmission line, that's just one of the phases of the three. And in some cases, you'll need to divide by 3, multiply by 3 if you're trying to compare apples to apples. If I give you the total load power and then I say the power in a transmission line, those are not the same. You have to either reduce one or increase the other to get them on the same playing field. Talking about totals. Don't forget that when I write a time domain expression, here's a voltage formula or equation, I'm assuming that that magnitude out in front is a peak magnitude. It's not in RMS units. You need to convert it to RMS units since it's a sinusoid, just dividing by the square root of 2 will convert it. And if you wanted the phasor form for little v of t, you would say, oh, that's 6 over the square root of 2 at 15 degrees. Another piece of information that might come in handy could be the omega. You might need that if you're now needing to find the reactive power associated with an inductor or a capacitor, since those involve omega. If you have to physically compute those, I may just hand that to you and say, oh, here is J7 for this inductor. Or I may say the inductor is L, and now I need you to find power. Well, that may involve using omega to find the impedance or the reactance associated with that circuit element. Line voltage. Now you have to pay attention to which terminals. If I say the line voltage, you need to know, where's he at? Is he at the terminals of the load? Is he at the terminals of the generator or the source? And at the load side, we usually use capital subscripts. And at the source or generator side, our subscripts are usually lowercase, alphabetical. There's line voltage. That's between two lines or two terminals of the line. It's not between a terminal and the neutral conductor. That's not what we mean by a line voltage. We have line current. That's simply the current flowing through a transmission line. One example is the A phase. That would be I from little a to big A. That's coming from the source and going to the load. And it's barred, meaning it's a phasor. It's a complex number. It's not just a single number. We're doing more than working all resistive circuits. Phase current depends on what the connection is. If we have a Y connection, then the phase current is actually the same as our line current. It's I sub little a big A. But if we have something delta, something being either a generator or a load, that could be connected in a delta configuration. And then the phase current for the A phase at the load would be I sub capital A capital B. It's across that impedance in the A phase. You need to make sure that you're comfortable with those concepts because you need the phase current to calculate the power in a particular phase. And if you now have a delta connected load, you can't be using the line current unless you use one of our subsequently derived expressions that involve total power, and they use line voltage magnitude and line current magnitude. But in general, if you're now trying to compute a per phase complex power, you need to use the phase current for that particular question. Likewise, we have phase voltage. In a Y configuration, that's from terminal, let's say A, to the neutral. But if it's delta, then it's actually the transmission or the line voltage, the phase voltage, in a delta configured load. If you now have freedom to pick your reference phasor, now you can set that to having an angle of 0. If it's not specified, you might say, oh, I'm assuming my reference phasor is this voltage or this current. It might simplify your analysis. Yes?
So like an example of choosing a reference phase would be like if you gave us a problem about three-phase power and it says convert to a single phase equivalent, we could choose, like if it didn't specify anything, and say we could just assume, it gave us like a magnitude, we could just assume that the angle's 0.
Yes, so the question was, is an example of a reference phasor if we had a three-phase circuit and I ask you to find a single-phase equivalent. You might be working through and you've been given magnitudes in that problem statement and you say, oh, I need to generate a generator voltage and nothing else has a phase attached to it because all the other things are impedances. Let me just use that as my reference phasor. You might just say, here's the magnitude of my generator voltage at an angle of 0. That's fine. Because I don't have to know anything really about the phase of that, or unless I start asking you, now what's the current that you might compute from this question?
Is it basically saying like you're choosing the A line or the A portion of a three-phase?
The question is, are you choosing the A phase? Typically, we find a single phase equivalent, we usually focus on the A phase, but you wouldn't have to. You could pick a B phase or a C phase. If it's balanced, it won't matter unless somebody starts asking you phase relationships among the different phases. And then you would have to say, oh, I need a reference phasor. Let me pick this particular voltage or current to be my reference phasor. And then everything would be related to that reference phasor. And know when phasor quantities and numerical values I'm meaning are magnitudes, are used in various formulas. Here are some examples. Ohm's law. That's a phasor form. V is equal to Zi. We've now generalized Ohm's law. And that involves complex numbers. Z is in general complex. Has a real part and an imaginary part. But we could also break things. I think I did. And take the magnitudes of all of those terms. We may just be done. So far, so good. We'll see how I can write with a crooked tip. But that's another way to work on phasors and just magnitudes. Likewise for complex power. That's VI star, where the voltage and currents need to be your phase voltage and phase currents. We could work with the apparent power, and then we're only worrying about magnitudes of voltage and current. Here's the expression that I was referring to before, the power, the total power expression. V sub L and I sub L, I may get sloppy and not necessarily always put bars over things, but here I'm intentionally not putting a bar over those. Those are just magnitudes. That's the magnitude of the line voltage, that's V sub L, and it's the magnitude of the line current. Typically, we don't work with those two in combination if we're talking about complex power, because it depends on the configuration, but we never have line voltage and line current always consistent. It's different in a Y and it's different in a delta. You have to use one or the other, not both of line. But here, for the total real power, and you could also view this for the total reactive power, it's square root of 3 VL IL sine of theta sub phi. Theta sub phi is what? Theta sub v is theta sub v minus theta sub I, but what's theta sub v and what's theta sub I? It's not the angle of this transmission line voltage and the angle of this transmission line current. It's associated with the impedance, or it's associated with the phase voltage and the phase current. It's not 30 degrees. So this theta sub phi is the angle of the impedance of that particular phase in your load if we were at the load side. Or it's the angle between the phase voltage and the phase currents, or the phase of the phase current and the phase of the phase voltage. That's theta sub phi. And in this case, it is in fact magnitude of terminal A to terminal B voltage and the transmission line or the line current. Some things you might want to put on your sheet. This relationship of positive and negative phase sequences. And now you could simply, if you could put those on a dial, and if somebody gives you one or the other and they tell you it's a positive phase sequence, you can spin this to a line B at whatever angle it needs to be, and you can now see what A and C need to be. Or if somebody gives you the A phase, you can now rotate this. Whether it's positive or negative will influence how the B and the C phases are related to the A phase. But from this diagram, let's just look at the top one. I think you can see that theta sub B is theta sub A minus 120. If you plugged in the angle for theta sub A of 0, you better get the angle of the B phasor. And you do. Theta sub B is at an angle of minus 120 degrees. Likewise for the negative. You need to keep that clear. And I would say just sketch it if you don't have it sketched. And then you can show or think through how they're related. That way you don't have to try to do everything in your head. You just sketch it down and you go, oh, this is how they're related. And move forward. Voltage transformations. If you're now going from line to phase in a Y-connected load, this is what you would do. You would just do a KVL and you have minus V sub AB. What? That's not right. I was going to do KVL. I'm just making sure that you're staying awake. maybe what I should have done is say minus V sub AB plus V sub AN minus V sub BN is equal to 0. And that now allows us to, we can use that generally, but what it translates into depends on whether you're dealing with a positive or a negative phase sequence. If it's a positive phase sequence, then V sub AB is leading or ahead of the phase voltage by 30 degrees, and it's increased by the square root of 3. Again, you could have this on your crib sheet. If it's the negative phase, then it's an angle of minus 30 degrees relative to the phase voltage. Current transformations all hinge around this picture, where now we have line currents going into a delta load. If it was a Y load, phase current is the same as our line current, but here KCL says, oh, the sum of the currents in I sub AA plus I sub CA is equal to the current out, I sub AB. And now that says, oh, this line current is made up of two phase currents. And that now gives us this relationship phasor-wise relating the line currents and the phase currents in a delta configuration. And those depend on whether it's a positive phase sequence or a negative phase sequence. And if you need to convert from one or the other, this is how you would do it. Questions on that? Yes. Pardon? I didn't hear what you said.
Can I just write it down real quick before you move on?
Sure, but I'm going to post this on the website so you'll have it. Hopefully. Yes.
So back to when you mentioned the power total, you say the line voltages and line currents, but that's not related at all to like the line impedance anyway, or?
So the question was, are the line voltage and the line currents related to the line impedance? I'm assuming that you now have calculated, maybe from a single phase equivalent, those particular quantities, your line current and your line voltage. You now have those, and those would obviously depend on everything in your circuit. So they depend on whatever is in your circuit. You might have to compute those, but once you have them, then you can plug them into that formula. You now have a line voltage and a line current. Boom, you can put those together. So if somebody now gives you those quantities, you could solve for one or the other. As an example, I think there's actually, let me see if I can do this. Here's an example that illustrates that. This is, I believe, from the Fall 15 practice exam. Here, suppose, and this is problem 7, suppose the magnitude of the line current feeding a balanced three-phase load is 2 amps. So there you're given the line current.
Right.
If the power factor of the load is 0.9 lagging and the load consumes a total real power of 500 watts, find the magnitude of the line voltage at the terminals of the load. That particular problem, when you kind of sit there and mull it over, it's begging to use that formula that I put on the screen earlier. This says total real power. The total real power is P sub T. And we know that that's equal to the square root of 3, boy, I am going to have problems. V line, I line, cosine, theta sub phi. And what are we given in this particular problem? We're given the power factor. Here's the power factor. We're given this current. We're given this total power of 500 watts. The only unknown remaining to evaluate is V sub L. That's a pretty straightforward question. But that's an illustration of, here we were given that information. If you were not, if you had to start solving for some of these quantities, you would have to evaluate, oh, what is my line current? And maybe in the single phase equivalent, you find a phase voltage, V sub capital A capital N. If you wanted to now use this, you would have to convert that to a line voltage. But if you're only worried about the total load power and you have the line current, or that which is in the single phase equivalent, that's your phase current. And once you have the phase voltage, you could find that phase's complex power by VI star. Multiply it by 3 and you have the total complex power of everything. Yes?
To remind me, does this power formula relate to both Y three-phase loads and delta three-phase loads?
This particular expression is independent of the load connection. You can use this whether your load is connected. So the question was, does this depend on how the load is interconnected? And it does not. This is independent of whether your load is in a Y configuration or a delta. You can derive this expression if your load was connected in a Y or if it was connected in a delta. You'll always end up with this expression. I'm guessing that another question might be trying to extract a single phase equivalent from a word description. And now this problem is asking just that. It's sketch a single phase equivalent for the following: three-phase balanced, good, it's balanced, and the system must be expressed in terms of voltage sources and impedances. You can't leave something as a power somewhere, and that might be what you're given. Here, the generator has a positive phase sequence. That really isn't even important in this problem. That's extra information, unless we needed to start interrelating different phases. But what I might do is I might just quickly say, oh, here's in general what I'm looking to find. Z sub G, Z sub L, and Z sub capital L. Always helps to have a spare. Let's see if this one works. Not that my handwriting is very good anyway, but I was feeling like I was really doing bad there. But that was with a bent tip. Let's see if we can do better. So now what do we have? We need to find these different pieces. We need to find the generator voltage. We could assume it's the reference phasor, so we don't really need to worry about its angle necessarily. But we're told that the generator is supplying a total apparent power to the inductive system of 1500 VA. What are we given so far? in that first sentence?
The total to the three phases.
The total. And what kind of power are we given? Apparent. What's that representative of? If this is the generator, so the generator S, uh-oh. That one doesn't even have a battery, apparently. So let's see if I have any nails. This is called engineering problem solving, and let's see if this now works. So now we have S sub G. But we don't have S sub G as a complex power. We have this, don't we? And we're told the total. And this is now 1500 volt amperes. So if we wanted that per phase, apparent power per phase, that's pretty easy to find. What is it? Just divide by 3. So this one is now 500 volt amperes. Assume there is no internal impedance in the generator, so this is now 0. We don't need to worry about that. That's now just a straight line between little n and the generator voltage. Suppose the line current magnitude is 5 amps. Now we know that this magnitude is 5 amps. And what else are we told? The real power absorbed in each oh boy, we're mixing totals, and so that's why it was nice to maybe immediately say, let's just look at one phase of this, and one phase of the apparent power of the source is 500. Now we can sort of compare that with this power absorbed in the transmission line is 50 watts. What we can always use is the fact that S, no matter what S is VI star. And in this case, if it's for the transmission line, we could say, oh, that's little l and little l. And in this case, let's now get rid of the voltage. We don't know that dropped across the transmission line between little a and capital A. But we can say, oh, that's Z sub L, I sub L star. Or this now is Z sub L, I sub L magnitude squared. When we have that, we were told that. Z sub L, we haven't been told everything, but we do know that this will be of a structure like R sub L plus JX sub L. And we are told the P, the power. This is now, if we expanded this, there's our power in a transmission line per phase. And we were told what that was. We said that's 50. And we were told that this magnitude of our transmission line current was 5, wasn't it? So now we know that 5 squared is 25. We can actually solve for R sub L. We're now saying that P of L phi is 50, which is R sub L I sub L squared, or R sub L times 5 squared. We have 50 divided by 25 for the transmission line impedance. Now we have one piece of our puzzle. We need R sub little l, X sub little l. We need R sub capital L and X sub capital L, and we need the voltage on our generator. We have one of the pieces. What else do we know? We know the total real power absorbed by the three-phase load is 600 watts, and the total reactive power of the inductive load is 600 VARs. Can we think of that in terms of per phase? We can divide both of those by 3, and we now could say that S load per phase is now 600 divided by 3 plus J 600 divided by 3, or it's 200 plus J 200 volt amperes. And this is R capital L plus J capital XL times I sub L squared. Isn't it? And we know what this I sub L squared is. That's 25. That's the same transmission line current. And we know that each piece, the beauty here is that we can set the real parts equal and the imaginary parts equal and end up with a value for R sub L and X sub L. We know that we have 200 plus J 200 is equal to R sub L times 25 plus J X sub L times 25. So how many quarters are in $2? Apparently not any. Question?
Yes, so on the test, obviously this is dependent, but if it doesn't specify, can I leave it in polar form as opposed to rectangular? So can I leave it in Z form as opposed to J plus?
So the question was, can I leave it in one form or another? I would beg to argue that for the single phase equivalent, let's pull them out into rectangular form. So in working these problems, you may want to think sometimes in terms of polar form and sometimes in terms of rectangular form. But for the single phase equivalent, I'm really looking for the real component and the reactive part of my impedance in both the load and the line. So I need you to pull those apart and put it from polar, if they were in polar, into rectangular form. In this case, we have 25 into 200, which goes 8 times. And that's now the same for R sub L and X sub L. In this particular case, you should have expected that because you had the same value of real part and the same reactive part. You have this 45-degree relationship, or equal real and imaginary pieces. Here, now we have R sub L and X sub L. R sub L is equal to 8, and X sub L is equal to 8. And that's now Z sub L. What else do we have? We've now found this. We have part of this, don't we? We need the reactive piece of the transmission line, and we need to find the voltage of our generator. Yes?
Can you, I don't know if this was on the solution line, but I think one way of doing it is take the reactive part of the generator, which equals a reactive part of the line plus reactive part of the load, and figure out the reactive part of the line that way.
What you may need to be doing is starting to look at all of the pieces and seeing what pieces you have and which pieces are missing. In this case, we were given the apparent power supplied by the the generator. We know that. We know the magnitude of our current. Does that tell us anything about the magnitude of our voltage? So we now have, we know that, whoops, S, what were we calling it? G, phi, magnitude, was that 500? And we know that the magnitude of I line was 5. And we know that this is true. Let me say phi G and G phi. Right? And can we use what information we presently have to help solve for what is the phase voltage of our generator in our single phase equivalent? Isn't it V sub A n? And this we know, we could say that that's V sub, or I sub AA. We just know its magnitude. We know the magnitude of S sub G, but we can now use all of those magnitudes to find the magnitude of our generator voltage. Meaning, from this, we can say the magnitude of S sub G of phi is equal to the magnitude of AN times I sub AA's magnitude. And that's now 500 divided by 5. And if we allow that to be our reference phasor, now we have the generator of our single phase equivalent. And what do we have remaining? So the only thing left is the reactive piece in there. Yes? So that VAN is what? Is it the line voltage or is it the phase voltage? So what did we have to do? If this is our complex power, here, what do we know has to be true with those voltages and currents? It has to be the same. They both have to be phase values. So V sub G phase is the phase voltage, and we're now in our single phase equivalent. That's being extracted from a YY configuration. This is now the phase voltage. V sub G phi is V sub AM. That's the phase voltage. That's not a line voltage. And I sub G phi is I sub AA. That's a phase current, which in fact is our line current because it's a YY. Yes?
The problem didn't state whether the generator was in a delta or Y configuration, so maybe that was like...
So the problem didn't state whether the source was in a delta or Y, but did it matter so far with what we've used? It didn't really matter, so we haven't needed to assume what the interconnected structure of our source was. We were not given any information that depended on the interconnection structure of our source, so let's just work with it already existing in this Y configuration. We just know that the total power, apparent power, supplied by the generator is 1500 volt amperes. And we can get that however we want. Other questions? And the solution really just now says, oh, we have the reactive power and we have the real power. We know the totals. And the only thing we don't know yet is the reactive power of our line, but we know the load's reactive power. We know we can find, because we're given apparent power and where was I thought, we didn't have the power factor here, but we can get the power factor from the triangle, right? We have the total real power of the let's say we have the real power in one phase and we have the apparent power. We can now use that to get the power factor of the generator. And once we have the power factor of the generator, we can get its reactive component, and now we can compare those two pieces, the reactive total with the transmission line reactive and the load reactive, to solve for the transmission reactive, and then use our relationship here that basically says X sub L is I squared, and that's equal to Q of L in that phase, and solve for X of L. That's on the solutions. What else do we want to look at? What other problems? Or do you have questions? Yes? Another one like this. I didn't bring one like this, but I would suggest that you look at some previous exams, and they're on previous exams, to give you some examples. Yes? Can I do a maximum power? I can. You know what one of the questions was on? Let's see. Where was it that I wanted to? Power factor correction. So maximum power transfer is really just saying the impedance of my source is the conjugate of the impedance of the load. That's maximum power transfer, right?
For the last homework, it was like an equation to use, and then if it was pure resistive, you have to like adjust the balance or something.
So maybe it's maybe a little bit like this. This one is basically saying, can we introduce a reactive component to wipe out the inductive piece of our load's power? This particular problem says, let's say we have a single phase system, find the reactive power supplied by a capacitor that is added in parallel to an original load. And suppose you want the power, so here they're giving us the original load absorbs 20 VA at a power factor of 0.8 lagging. What's the original? So here's the picture. Whoops. We have an original load, but we want to eventually put in another load that consists only of a capacitor. And the addition of that capacitor is such that we want to modify the reactive power that existed in the original load. Now, we're not given the reactive power directly in this particular problem, but can we obtain it from the given information? So the question was, does it matter that P is or isn't changing after we add the capacitor? It's important to figure out what we need to solve for. If we have a pure ideal capacitor, we're assuming we are not changing the real power absorbed by the load. It's only changing the reactive power. What is our reactive power? So now let the original load absorb 20 volt amperes at a power factor of 0.8 lagging. What's the 20 VA? Real, reactive, complex? So 20 volt amperes, that's the apparent power, isn't it? That's the magnitude of your complex power. So if we call this, let's say SL, we are now given and we're told that the power factor is 0.8 lagging. Meaning we could say something like, oh, the power of the load is now S sub L cosine of theta sub L, but this is just the power factor. We're told that this is 20 and this was 0.8. So now we know that the power of the original load is 16 watts. Yes?
So every time I give him the power, the complex power, or I see the complex unit, that means the apparent power.
No. So the question was, every time I'm giving, I think you're asking, every time I see VA, does that mean it's apparent? I could have actually written it in terms of magnitude and angle, or I could have written it in terms of rectangular form and still use the units VA. So I could have said something like 16, and how big is the Q going to be of the original load? Can you tell me just by inspection of the information? It's 0.8 lagging. Is my reactive power of the original load bigger or smaller than the real power?
If power factor is greater than
Do you know what I'm asking? If my reactive, if my complex power was like this, I wanted those to be equal. So let me draw them maybe. This is now Q and this is P. And if those are equal, what do you know this angle is? And what's the cosine of 45?
1 over square root of 2.
Or it's the square root of 2 over 2. I know the square root of 2. That's 1.4, and I can divide that by 2. It's 0.7, right? So it's 0.707. Our power factor is bigger than that, isn't it, in magnitude? It's closer to 1. So what's that tell us about the angle theta of the original load here? Is it bigger or smaller? If theta was 30 degrees, what's the cosine of 30? Square root of 3 over 2, 0.866. So that's getting closer to this. And what did I say? 30 degrees. So now we know that we're between 45 and 30 with our theta. If we're now between 45 and 30, how big is Q relative to P? Is Q smaller or larger than P? Smaller. So now if you're doing this and you end up with a Q that's bigger than 16 for the original load, you go, whoa, 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 wait. I did something wrong. Just by looking at this 0.8 number. if that's 0.8, actually Q of the original, you could find this many different ways, however you want to do it. We now know that cosine of theta is 0.8. You could solve that for theta, if that's how you like to think. And this will be, this is that 36 degree angle, isn't it? This is the 36.87 degrees. And so our thought process of being between 45 and 30 is right on. It's between 30 and 45 to give us this 0.8. Now we can find, we were given this, we could now find QL. That's SL sine of theta. This is now 20, and the sine of 36, that's 0.6, or this is now 12 volt amperes reactive. That's now Q of the original load. And so our triangle so far is 16, and this was inductive, wasn't it? And now what do we need this to end up with? We now need to add a if we wanted to get a power factor of 1, what would the capacitor's reactive power need to be equal to? If we wanted a power factor of 1, what would we want the angle to be? Right now, this is the original load, and this is 36.87 degrees. If we wanted a power factor of 1, what would the reactive component of our capacitor have to produce in terms of power? You would want your capacitor to give you 0. You want to cancel something out. You want theta sub L, or theta of the total, to be 0, don't you? You want your angle to be all the way down to 0 degrees, which means you need to move that 12 to minus. You want your capacitor to give you minus 12 reactive power. In this problem, is that what it asked? Does it want a power factor of 1? So if we wanted a power factor of 1, then we would want, I'm mixing my colors, but we would want that capacitor to bring you down here to give you a minus 12, to get you to 0. In this particular problem, it says, suppose you want the power factor after adding the capacitor to equal 0.95 leading. So now it wants us to go even beyond 0 and go even further. So now we know that Q of this capacitor needs to be bigger than minus 12. How much bigger? In magnitude, it needs to be bigger than 12. Wow, this is... And we now need to be somewhere down here. And where do we draw that dot? How do we know how far down to go? Can we figure that out from the given information? Okay, yes. So now, correct answer. I just need more information than a yes or a no. So yes is correct.
So if we take the arc cosine.
So now we need to basically find, how does that 0.95 translate into an angle? Yes. We take the inverse cosine of 0.95 and we'll get an angle that will tell us, in fact, where we need this dot to be. This angle theta, let's say total, is going to be the inverse cosine of 0.95. And that will be a negative value because we know we're leading. And one of the critical pieces of this is that we are not changing the length of blue. We're keeping blue fixed. And now we know that if we have blue at 16 and we have this angle, we can get this other side. And once we have this other side, that's all the more we need to go down from minus 12. Yes?
So would you want to find the Q after? So like you want to find the load of, because you're given the power factor after the.
You're given the power factor after the addition of the capacitor. You're essentially indirectly given this dot. You now know that, oh, you started 12 positive. If you can find this dot, if that dot, maybe I should look at the answer so my numbers make sense. Suppose that dot is now at minus 5.2. But you know it's down there somewhere. If it's now at minus 5.2, you can add that to, or subtract that from 12 to get your total reactive power that the capacitor needs to produce. It needs to be minus 12 minus the 5.2. That's the reactive power that you want your capacitor to produce or provide to end up with a power factor of 0.95. That problem's done, right? Stick a fork in it. We're moving on. Maybe. We're okay with that? You get the idea as far as what we want. Now, I could make it even another step, and I could say, what's the capacitor to give you that? What would you now do if I said, what capacitor value do you need to make this happen? In this problem, I'm just asking for Q sub C. And if you wanted partial credit, you would put a minus after that equal sign, right? You would say, oh, I know it needs to be minus because my original was inductive and I need it to actually be going below 0 for the reactive piece. But if I said, what's the value of the C to make that happen, do you have enough information to make that determination? We aren't given the frequency here, are we? Oh, we are. Oh, well, in this problem, we didn't need it, did we? But if I needed you to go on, they do have the frequency of our system as omega is 377. So you could use that to actually obtain your C value. But you might need to know a voltage or a current somewhere in order to get it. And you don't have it here. Any other questions? Are we finished? This projector is. My pen is. But I would encourage you to start looking at these problems. Here's a good one, meaning you need to understand how to start analyzing circuits. And in this case, if you're wanting power, you might want to convert things to RMS and in phasor form. This is a single phase circuit. And if you're given C and L, now you may need to use that omega, and the omega in this case is 20. And that will allow you to obtain Z sub L. Z sub L is now J omega L. Omega is 20 and L is 0.5. The impedance of my inductor is J10. The impedance of the capacitor is minus J5. And R, is it given? It's 5 ohms. And there's all sorts of ways that you could analyze this problem. But you need to, at some point, maybe find the current through that resistor, and then you could say, oh, the magnitude of that current squared times 5 will give me the power. However you want to try to find that current through this branch that includes the resistor depends on how you visualize or solve this circuit. You might start writing 2 mesh equations. That's maybe the more involved way, but it's maybe the more automatic way for most students. But that gives you 2 currents that you have to now solve for. You could solve for the node voltage or the voltage at the top of R and C. And now you just have one unknown variable, a voltage, and you'll now need to relate that voltage to the current going through that middle path. But once you have that voltage, you can find that. And just a couple of ways of, or thought experiments, or thoughts on that sort of tells you, oh, I can do it with 2 meshes or 1 voltage. Maybe I just want 1 voltage, 1 equation, instead of coupling equations. And boom, now you've defined the direction you want to approach that problem solution in. Yes? You want me to start writing some equations? What I'm saying now is, suppose that we wanted to solve for that voltage, and it's going to be a phasor. Now we have, and what's VG as a phasor?
It's 7.07 angle 0.
And if we want to do power, what would I do? That's now in maximum value, isn't it? I would probably take that and divide it by the square root of 2 to get all my phasors in RMS form. I would probably divide this by the square root of 2. In grading this, you would be surprised how many students took the 0.707 and treated it like it was RMS, and so their answer was off. And it's natural to do that. But so the first thing that you might want to do when you see, oh, he's given me a time domain voltage, whoa, let me convert that into a phasor and let me switch that amplitude or that maximum magnitude into an RMS. And now I can play with that. I now know V sub G. I know the impedance of my inductor. I know the impedance of my capacitor, and I know the resistance of R. I can now redraw that, and I would not be trying to think of these all in my head all the time. I would just say, oh, let me redraw this. This is what? This actually simplifies to 5 at 0 degrees when you divide 7.07 by the square root of 2. This was J10. This was 5, and this was minus J5. And what I'm wanting to do is use that voltage or solve for that unknown voltage, where this is now plus and minus. Or I can now say, oh, I have this current, and that current flowing out of that single node, and those currents are going to be defined in terms of that unknown voltage V sub 1. The horizontal current going to the left, defined by the way I've labeled these, it's now V1 minus 5 over the inductor impedance, J10. Plus, all of these currents are leaving. I'm going to just sum them all and set them equal to 0. I have V1 divided by 5. And last, I have V1 divided by minus J5, and those are all equal to 0. And if you go, oh my, I'm feeling anxious about doing complex arithmetic, move on and just get your confidence up and say, I'll come back to this. This equation is correct. I just have to slow down and do the math and solve for V1. And then what would you do? If you know V1, how do you get the power absorbed by that 5 ohm resistor? If you know V1. Pardon? Why can I not hear today? I can't hear in general. So you could say, if you have V1 bar, you know what IR is, right? IR is now V1 bar over R. And the power of that resistor is VI, or you could say in general the complex, but you now know that it's R times IR squared. And if you know IR, you now have this, and you know V1 over R, and these are all magnitudes squared. Or you now know that if I take the magnitude of V1 and square it, the magnitude of a real number is the real number, and I have R squared downstairs and R upstairs. I now have R downstairs. If I now know V1, if I solve for V1, I can find its magnitude, square it, divided by 5, and that's going to be the power of that resistor. And you could do this without solving for V1 and get a lot of points, partial credit-wise. Then you would come back and say, oh, I need to solve for V1. But do you see the thought process? Now you go, oh, it's all laid out. I have my map in front of me. I can now start solving this when I have time for V1. And that is simply going to involve some complex algebra. Is that okay for a solution? Yes.
I have a problem, but this is from the practice. This was from the fall 2013 practice exam. So it's this one. But I want to talk about a certain wording that they said about.
So the question is some problem from the fall 13 practice exam, and it looks like it has a generator, a transmission line, and a load. Is it single phase?
It's this one. What I'm confused about is it says the real power absorbed, or no, wait.
Says the real power absorbed in each transmission line equals 20 watts. Is that right?
Oh no, it's this one. Sorry, the line voltage magnitude.
So the line voltage, I hate to take your computer. The line voltage magnitude, because I felt like it was attached. The line voltage magnitude at the load terminals is 156.8. So what am I telling you?
So I used to think that was the voltage across, the voltage drop across the line impedance, but I looked at the answer and it wasn't really.
No, so now what I am giving you in that, what was it? Fall of 13, some problem. I said the line voltage magnitude. Whoa. I'm now going between point A and point B. Did I say it's at the load or at the source?
At the load terminal.
So now I'm giving you this voltage, and in a single phase equivalent, that's not what you're looking for, is it? You now have an impedance. If it was Y connected, you have Z sub A, and you have Z sub B, and here's neutral. And I'm now giving you the magnitude of that. But you could convert that, if everything's balanced, that's now where you would use your voltage transformations and say, oh, I can convert that now to a phase voltage to get maybe some values that I can use to find impedances at the load. That's why I said you need to pay attention to what's being stated, whether it's saying total, whether it's saying line, whether it's saying phase. But if I say line, it's now between terminal A and terminal B, either at the load or at the source. And you now, if you need phase voltage, that's not the phase voltage, is it? For a Y-configured load. You would then have to, you know the relationship magnitude-wise, it's a square root of 3. And you could now find this A phase voltage by dividing by the square root of 3 for its magnitude. And that might be what you need to start approaching that problem. You don't want to assume anything. It's worded, and if you do think you need to assume something, you could say, I'm assuming this. But if you say, I'm assuming this is the phase voltage, I'm going to say, well, that's wrong. That's not correct because I defined it to be the line voltage. So it's from terminal A to terminal B.
It's not the line impedance. It has nothing to do with the line impedance.
It has nothing to do with the impedance in the transmission line. That's correct. So if I said something like the voltage dropped across the impedance of the transmission line, that's different. But if I say the line voltage, it's now between terminals A and B, and whether those A and B are capital or lowercase depends on whether we're at the load or at the source. Okay? We'll assume that's good. And we'll look for everyone to be here. Get plenty of sleep. That's probably more important than studying all night. I know it's more important than studying all night.